Swayam Prabha. Digital India. Educated India.
Let us start our today's lecture for NPTEL video course on Geotechnical Earthquake Engineering. We are going through now module 8 of this course, that is Site Response Analysis. Now, let us have a quick recap what we have learned in our previous lecture. Like we started defining what is called transfer function. It is nothing but a filter or a multiplier which changes input ground motion to an output at another level. So, we have seen various cases how to estimate the transfer function, like for uniform damped soil, this is the way we calculate the transfer function, and this is the transfer function expression, which is nothing but the ratio of the displacement function at ground to that at the rock level, that is interface between the soil and rock. Then we have seen what is the expression for this transfer function, which is a function of the frequency and the damping ratio expressed in this pattern. So, which is nothing but can be mentioned as amplification factor in terms of kH. So, we can see as the damping ratio increases, the amplification factor will decrease, and so on with number of cycles. Then we have talked about uniform undamped soil on an elastic rock. Earlier we talked about rigid rock, and then we came to consider the elastic rock, which is more practical. For that, we have seen, even though we do not consider the damping of the soil, that is the material damping or the viscous damping of the material we had considered, but even then, because of the impedance ratio of non-zero value between this elastic rock and the soil, you will get the non-infinite value of the transfer function at the particular value of kH, like this. So, this is the expression for transfer function when the specific impedance ratio between the soil layer and the rock layer is considered, that is considering the elastic rock. Then we have talked about most generalized case of layered damped soil on elastic rock. So, for that we have seen that the displacement compatibility and the stress equilibrium between the layers has to be maintained, which by known boundary condition will give us the values of various coefficients. Then we have also discussed how to carry out the equivalent linear ground response analysis. This is how the modulus reduction curve or G by G max ratio over the cyclic shear strain varies when we are talking about G secant, that is secant modulus, and the how the damping ratio varies with respect to the cyclic shear strain. So, we need to choose initially one initial value of the cyclic shear strain to start the analysis, and until the results of assumed strain and the final output strain after using the chosen value of G and eta we get matches those two strain, we have to repeat this. So, this is a trial and error procedure or iterative procedure by which finally we will get that gamma effective. However, for nonlinear approach, we cannot use that modulus reduction curve. We need to then use the equations, solve the wave equation incrementally, that is a small steps of the backbone curve of that shear stress versus shear strain into a small time interval steps. Now, to do that, these are the steps we have seen. We have to start with initial tangent modulus, which is nothing but G max, then use small time step of delta t, that time step has to be chosen based on the entire time duration of the input ground motion or input seismic motion, wherever level we are considering. That time has to be subdivided into number of small time segments. Then you have to compute the shear strain amplitude at the each end of time step, that will give the corresponding G tangent, that is individual tangent modulus for each and every time step. That finally will lead to the shear strain amplitude at the end of each time step, and it has to continue for the entire time duration. So, by using this incremental procedure of analysis, we will get this backbone curve of nonlinear response, which automatically considers the material damping by this hysteretic response, and this approach requires a good model to understand the behavior of this stress strain. So, what are the good models? Two major types of models, one is cyclic nonlinear model, another is advanced constitutive model. Now, cyclic nonlinear model one can get very easily from a lab test on a particular soil by knowing the backbone curve, unloading reloading rule and the pore pressure model, whereas for advanced constitutive model, yield surface, hardening rule, failure surface and flow rule, all this information should be available. So, we have seen also in our previous lecture a comparative study between the use of cyclic nonlinear model and the advanced constitutive model. We have mentioned that obviously the cyclic nonlinear model is a simpler model to use, but there are difficulties like exact soil behavior or dilatancy effect etc. may not be captured, whereas advanced constitutive model is the best that way, because it considers all the dilatancy effect, yield behavior, failure behavior, everything, but the disadvantage is it is a complex model and it requires longer time. Also, it is difficult to calibrate with respect to a particular soil model. That is, unless for your soil you have your constitutive model known, then otherwise you cannot use this advanced constitutive model for your analysis. Now, in today's lecture, let us now start with the comparison of this equivalent linear and this nonlinear site response analysis. So, inherent linearity can lead to spurious resonances in equivalent linear method. What inherent linearity we are considering? If you look at this curve once again, which we have already discussed in previous lecture, this is the inherent linearity which we are considering, right. It is actually non-linear, but we are assuming this linearity. So, that inherent linearity which is used in equivalent linear method may lead to some resonances, spurious resonances, which is not actual. So, use of this effective shear strain can lead to over damped or under damped system depending on the nature of strain time history. Equivalent linear analysis can be much more efficient because it is more faster, right, than nonlinear approach, whereas nonlinear analysis can be performed in terms of effective stresses, and nonlinear analysis can predict the permanent deformation, because it is exactly capturing the final cyclic shear strain which the material is undergoing through for that time duration of input motion. So, what will be the suggestion for a practical use of this equivalent linear or nonlinear approach when we are dealing with very important problem, let us say design of any earthen dam or design of some nuclear power plant foundation system. In those cases where the importance of the structure is very high, in those cases nonlinear ground response analysis is a must, whereas for medium important structures or medium important analysis like for buildings etc., if you want to do the ground response analysis, what you can use? Equivalent linear approach. Why? Because equivalent linear approach will save a lot of computational time which is necessary in case of nonlinear approach, because you are doing incremental small time interval and repeating the method of analysis. So, that is why nonlinear approach takes much longer time of computation than equivalent linear analysis. Also, nonlinear approach is complex than equivalent linear approach, whereas I am telling that linear approach, where only Gmax is used, should be avoided for any type of ground response analysis, because we know earthquake response is a high strain phenomenon. So, in that case, if somebody is using linear ground response analysis, that will be absolutely wrong, because that does not capture the high strain phenomenon. It will be only a low strain phenomenon where Gmax is valid or linearity of the model is valid. Okay. Now, let us look at this comparison once further. That is, nonlinear analysis require reliable stress strain or constitutive model, which we have already seen. So, this is one complexity in the analysis. Differences in computed response depend on the degree of nonlinearity in the actual soil response what it is having. So, suppose if we are handling with stiff soil site, that is, these are all relative terminology of course, with weak input earthquake motion, in that case nonlinear and equivalent linear will result almost the similar output. That is, for a stiff soil site and subjected to weak input earthquake motion, you can either use equivalent linear or nonlinear. In both the cases, similar results you will get. So, obviously, it is better to use equivalent linear, which is less time consuming, also which is simpler to analyze. Now, but for soft soil site, where chances of liquefaction is there and the soil site is subjected to strong input motion, in that case nonlinear analysis is always preferable, because that will capture the actual displacement of the soil material, which will help you to further calculate the displacement related to this liquefaction, and which will lead to lateral spreading, etc. Right. So, those things, for those type of soil site and that type of input motion, strong input motion, non-linear approach is preferred over equivalent linear approach. So, some practical aspects of this site response analysis, what we can say, that equivalent linear much more commonly used. Why? Those are commonly maximum used than non-linear, because of its first widely available method, because it is pretty well known and widely available. Greater range of experience, many people have done. So, people have experience handling with that. Performance is well documented, how they perform with the equivalent linear approach, those are available in literature. It generally runs faster, because less computational time than nonlinear. It allows deconvolution. What is deconvolution? We will see that. Convolution is nothing but when we are approaching from the ground to from the bedrock to ground surface, and deconvolution is the reverse one, that is from the ground surface to the bedrock level. Material property characterization is easier in case of equivalent linear. Why? Because only you are considering the G secant. At whatever strain level you are interested to, that value of G sec you can consider, right. Wherever we are mentioning this advantages of equivalent linear over the non-linear, what are the other side of it is probably these are overused for the case of very soft site and liquefiable site, which should not be. We have already seen for this type of site, non-linear approach is better, nonlinear site response analysis or nonlinear ground response analysis is a better option. Now, practical aspects of the site response analysis are convolution. What is convolution? As I said just now, bedrock motion is applied at bedrock level, and outcropping motion needs to be obtained. Motion within the profile has to be obtained and motion propagated upward through the soil profile. Whereas, what is called deconvolution? In this case, motion is applied at the ground surface, and then that motion propagated downward through the soil profile, and bedrock motion corresponding to surface motion is computed in this case of deconvolution. So, for the case of convolution, we need the transfer function to be used, whereas for the case of deconvolution, we need to use the inverse of the transfer function to be used, right. Now, as we have already discussed these common situations, two major common situation and how to find out. Now, after having the complete knowledge of this site response analysis, let us look at it once again. That is, common situation 1 is, say, ground surface motion on the top of some soil layer needs to be determined. So, at this point we want to obtain, that is the problem statement, let us say. So, determine the soil profile characteristics. We need to know what are the material property of this soil layer by subsurface investigation or the field or laboratory testing program. Then determine the design motion characteristics. How we can get that design motion characteristics? Either using deterministic seismic hazard analysis or probabilistic seismic hazard analysis, right. And site conditions must be recognized. What type of site? Then obtain the input motion. Obtain input motion means for which earthquake motion you want to analyze, you want to carry out this ground response analysis. Like actual input motion you can download from the website, that is for the authentic data, as I have already mentioned, USGS database or IMD database or PR database. There are various other database where actual ground response or actual earthquake response at different depths are available. So, you can use that motion as an actual motion, or one can use the synthetic input motion. Synthetic ground motion is nothing but it needs to be generated. You generate it is synthetically designed, it is not the actually happened, and this actual is where some earthquake has really happened in some part of world. And then using this input motion, whether it is actual or synthetic, outcrop or within the profile, that needs to be determined, that needs to be known, whether it is a outcrop motion or it is at the bedrock, right. So, then once we get all this information, what we do, say this outcrop motion you are getting from some website, if it is an actual earthquake from some reliable source, or you are applying some synthetic motion, you can do that also, because when you are doing site response analysis at a particular site for your design, you do not know in future what earthquake will come. So, probably either you can use the historical earthquake in the nearby region, or you can use some synthetic motion which will justify the seismic zonation of that area. Okay. So, that way the synthetic motion has to be chosen at outcrop. So, this is known. Now, this motion and this motion should be different. Are this motion at 2 points identical? No, they cannot be identical, because it is a free surface and this is a underlain by a soil layer, right. So, in one dimensional analysis, input motion is applied at a point directly below the ground surface of the point of interest. So, you can apply, if the bedrock motion is known, you can apply it here also, but that should be different, you remember that. Then you apply all the soil properties etc., do the either equivalent linear or non-linear analysis to get the known value over here. So, that is what it says. Here it is zero stress free boundary condition, whereas it is non-zero stress. So, that is why they should not be equal, as I said already. So, bedrock motion will be slightly different than the rock outcropping motion, because of it is related through that transfer function using that boundary condition. And equivalent linear programs allow specification of rock outcropping motion, bedrock motion automatically gets computed. Okay. So, this bedrock motion, once you put it, then you compute the free surface motion by using this equivalent linear or nonlinear programs. So, for that, as I said, either shake or deep soil can be used. For common situation number 2, where free surface motion at one soil site is known. Suppose just now we have computed at this soil site 1 the ground response analysis, right. Then in another soil site number 2, we need to find it out. Say soil site number 2, we need to find it out. So, how we can do that? We need to transfer from point A to corresponding bedrock motion point B, and that bedrock motion you have to take at the outcrop motion C. That C you have to take if the rock profile is same at outcropping at the two different places at ground surface also, because rock material is same and both are outcropping. So, you can use that data. Okay. Once you use that data at C, then from C, D you equate, that is assume that rock outcrop at site of interest D is equal to that of measured at C. Then once you get D, you can get it at E, again using transfer function. Once you know at E, then use the ground response analysis and get this unknown at soil site 2 F. So, compute the desired free surface motion at F. So, these are the steps how we carry out the ground response analysis or site response analysis from one site to another site. Clear? So, the deconvolution, how we can cross check, it is helpful to check the results carefully before using, because it may be unrealistic sometimes. Like soft soil profile, high frequency components are getting de-amplified, whereas for consistency with surface accelerations, unrealistically large high frequency bedrock accelerations may be required. So, in that case, to check the deconvolution, you can use the synthetic time history also, that is what it means. Instead, if you do not have a real earthquake motion, to check the deconvolution for your soil layer, you can use a synthetic time motion. So, it can filter surface motion below 15 hertz frequency to reduce the potential for this effect. Now, let us start going through the example problems on this ground response analysis from two case study. These two case study, the first example is the case study on the seismic ground response analysis for Mumbai city in India. This is a part of the PhD thesis work by Dr. V.S. Fanikant, who completed PhD in the year 2011 at IIT Bombay under my supervision. He is a scientist at BRC and Dr. G.R. Reddy was external supervisor from BRC. So, from his PhD thesis work on this ground response analysis, this journal paper has been published. So, one can go through this paper for the detailed discussion about how this ground response analysis using the equivalent linear approach has been carried out for some typical sites in the Mumbai city of India. This is in journal Geotechnical and Geological Engineering of Springer publication, volume 29, issue 6, page number is given over here, year 2011. Okay. Now, let us go through step by step for this equivalent linear ground response analysis for some typical site. 3 typical sites Dr. Fanikant had chosen. One is Mangalwadi site near Girgaon. There are 2 borehole data, typical borehole data. Mangalwadi site borehole number 1, Mangalwadi site borehole number 2 were used. Walkeshwar site, Walkeshwar borehole number 1, Walkeshwar borehole number 2, and BJ Marg near Pandhari Chaul site with BJ Marg borehole number 1, borehole number 2 and borehole number 3. Typically, these soil data from collected source of reliable sources of soil data, this information has been first taken care of. So, this is the typical borehole data for the Mangalwari site number borehole number 1. You can see the layer thickness over here given, depth below the ground level, that is beyond 9.8 meter below the ground level, the hard rock is available at that site. You can see over here. So, corresponding SPT values are given over here as recorded at the site. Based on this input motion, what next step we need to do? This is the bedrock. We have several layers of the soil as we have seen. So, that multi-layered site response analysis we need to carry out. What we have just now we have seen how to carry out for individual layer. So, to do that, next is we should know what is our input motion we are using. Now, for the input earthquake motion, Dr. Fanikant had chosen these 4 input motion: 2001 Bhuj earthquake motion, 1989 Loma Prieta earthquake motion, 1989 Loma Gilori earthquake motion, and 1995 Kobe earthquake motion. These are the various parameters which are obtained, like date of occurrence of this earthquake, magnitude, MW, recording station, distance from the source, that is MHA, predominant period, mean period, bracketed duration, and significant duration. So, all these data have been taken as input value of this earthquake motion for further ground response analysis at those borehole locations or soil site. So, once again the pictorial representation of this acceleration versus time history of the input motion. So, this first one is for the Bhuj motion of 2001 earthquake, then Loma Gilori, this is Loma Prieta, this is Loma Gilori, this is for Kobe. Now, input parameters for this borehole number 1 has been further extended to the shear wave velocity. Why we need shear wave velocity? We need shear wave velocity because unless we know the individual layers of soil shear wave velocity, we do not know the initial tangent modulus or the maximum shear modulus G max, right. Because G max we can calculate from rho Vs square. Now, this Vs either it can be estimated from the site using MASW or SASW or other field test, or in absence of that one can use the available empirical relationship between SPTN value and Vs value and obtain these values. Then starting point of damping ratio is considered as 0.5%. All these are 0.5% for all the layers. You can see 6 numbers of layers for this MBH1 as we have already seen has been considered. So, this is individual initial values of damping ratio for an initial cyclic shear strain. So, this is reference strain in percent initial values, reference stresses and other coefficients beta s and so on. So, you can get the details in this paper as I have mentioned, where you should know the equation for the backbone curve, that is tau versus gamma, which is expressed in this form. So, GMO is nothing but initial tangent modulus, that is maximum shear modulus. Okay. Beta is a coefficient, S is another coefficient, gamma is cyclic shear strain and gamma r is reference shear strain. That is, you select a reference strain at beginning and then do this iteration until this selected reference strain and the converged finally obtained reference strain matches. After doing that, what output you will get? So, this analysis was done using the software Deep Soil. Deep Soil version 3.5 beta of 2008 version was used. So, one can always use the latest version to do the analysis. At that time 2008 was the latest version. Final output one can get this acceleration versus time history at any layer. So, finally, for any structural design we will be interested to know the ground at ground level what is the output acceleration time history. So, this result shows the at ground level this is the acceleration time history of that 2001 Bhuj input motion, which was given input as the bedrock level at that borehole number 1 at Mangalwari site. So, using that soil property, using this, we got this one. So, this was your input motion. You can see the maximum value was 0.106 G, whereas the output came more than 0.2 G. Can you see that? So, there is an increase in the maximum value of acceleration from the bedrock level to ground level in that borehole number 1, considering the local soil parameters or properties. So, the response spectra, acceleration response spectra, if in that fashion we want to express, because why we are interested to know about response spectra? All the design codes, they talk about the response spectra versus period, right, that we have already seen even in our IS code also. So, this is acceleration response spectra with respect to this period for different earthquake input motion. For Bhuj motion, this dark color solid line, for Kobe this dotted one, for Loma Prieta this one, for Loma Gilori this one. Okay. So, depending on different input motion, your output is also different, as you can see. For the same borehole location MBH1 at ground level. So, this response spectra is at ground level, considering 5% damping at the soil site. Okay. Because you remember, whereas you are getting this acceleration time history result at ground level, here you are getting the exact damping ratio, but for spectral response spectra, you have to assume some damping, because it is for the equivalent single degree of freedom mass spring dashpot model, right. You remember for response spectra how we determine. So, that is what it is mentioned, 5% damping. It is nothing related to actual damping of the soil. You can see the result that Amax value, the maximum value at ground level for MBH1, what we got, it was about more than 0.2 G, higher than 0.2 G. So, that if you compare with respect to your input value of 0.106 G, what is the increase or amplification of peak value? Amplification is nothing but, we can see Amax in terms of G at ground level divided by maximum horizontal acceleration at bedrock level. That will give you nothing but the values of amplification with respect to depth. So, for different earthquake input motion and for all different borehole, all the borehole number 1 of all these 3 sites are reported over here. You can see in Mumbai city, typically considering all this soil site, we got a range of soil amplifications ranging between 1.2 to about 3.5. That is the range of soil amplification when we are considering a bedrock to the ground surface level. Clear? So, that shows a typical soil amplification of earthquake acceleration at various soil sites in Mumbai. This is in the tabular form, the exact values are computed, the same thing, MHA at ground surface by MHA by bedrock at different input motion and at different borehole site. Now, we can see acceleration response spectra at different layers. Can you see layer 1 is nothing but your ground level, which we have already discussed. But if somebody is interested to know that other layer, say layer 2, layer 3 or layer 6, why it is important? It is again for MBH1, but for different input motion. This figure A is for Bhuj motion, figure B is for Loma Prieta motion, figure C is for Loma Gilori and figure D is for Kobe earthquake motion. Why this response spectra is important? Let us look at very carefully. Suppose if we take this Bhuj motion for MBH1 at the ground surface, see where the peak is occurring at this time period. So, corresponding to this time period, whatever buildings or structure will be there, that will be more vulnerable or will be subjected to maximum damage. Am I clear? Now, if you are considering your structure, say you are constructing a foundation or underground structure, let us say close to your layer number 6. For layer number 6, you see here where the peak came here. Can you see over here? This is the peak for layer 6. So, when you are designing corresponding value of time period, that will be more critical. That is, a structure having time period of this value will experience maximum damage when we are constructing any structure at layer 6. So, that way individual layer wise data also very much helpful to us. So, this is about layer variation. Now, let us compare Bhuj motion with respect to Kobe motion. What we can see? For Bhuj motion, the major damage will occur, or the peak value of spectral acceleration we got at the period of say about 0.2 seconds, right. Whereas, for Kobe motion, the peak came same at top layer ground surface is about 0.5 second. So, that means it is not that all the same structure will be subjected to same amount of damage irrespective of ground motion, but it will be subjected to damage depending on what is your input motion. That is, Bhuj motion will make maximum damage to a structure which is having a period of 0.2 second, whereas Kobe motion, if it comes to Mumbai at that site, that will damage a structure which is having a period of 0.5 seconds. Is it clear how we are using these things for further design? Hence, it is very important, instead of generalizing, one should do a site specific ground response analysis like this, depending on various input motion at that particular site, or using a logical synthetic motion at that site to get the data for further design. This is the Fourier amplification ratio. That is, we know the response of amplification or acceleration we can express in terms of spectral response or Fourier response. So, this is in terms of Fourier response. Now, let us come to the values of this frequency, what we can compute using the simple formula of this sum of 4h by Vs that we have already seen, right. So, using that simple formula, that fundamental frequency what we can get, that comes out to be this, knowing the values of Vs and individual layer value of H for all your site. Now, deep soil software also will give you the corresponding values of frequency. Now, equivalent ground response analysis values of frequency output we got like this, and nonlinear ground response analysis we got like this. In all the cases, Bhuj motion is used. So, if you want to see what is the percent error or percent difference, I should not mention it as error. So, it is within the about 20% in case of equivalent ground response analysis, whereas if you use the nonlinear ground response analysis, it is still lower, it is within 13%, right. So, nonlinear result will be obviously closer to the actual values as it is expected. Now, let us come to the next example of ground response analysis, that is example number 2, which is the case study on the seismic ground response analysis for 4 port sites, ports in Gujarat state of India. This is a part of the PhD thesis work of Dr. Jayakumar Shukla, who completed the PhD in 2012 at IIT Bombay under my supervision, and this is the journal paper which describes about the details of this seismic ground response analysis of 4 port sites in Gujarat, that is seismic hazard and site specific ground motion for typical ports of Gujarat. It is published in the journal Natural Hazards, Springer publication, volume 60, issue 2, page number is given over here in 2012. Let us look at the major 4 ports for which the study was carried out. These are the 4 ports: Kandla port, Mundra port, the Hedge port and Hazira port. These are the 4 port sites, and these are the fault map. Already we have discussed it in the seismic hazard analysis problem. What are the steps followed? Like fault map and seismicity parameters are known, logic tree framework is already used. Then we have developed UHS at bedrock level for the synthetic ground motion. Then geotechnical characterization is now necessary for each of the port site to carry out the site response analysis, which will finally give us the result for this site response or ground response analysis. So, to do that, this is the UHS or uniform hazard spectra, which we have already seen for different return period of 2475, 72 and 475, and we have compared that with respect to IS code recommendation for zone 5 when we are talking about Kandla port, which is in zone 5 of seismic zone as per IS code. Okay. So, as we have mentioned, IS code value is matching close to our return period of 475 years. Similarly, you can use that for Mundra port site. This is the spectral acceleration versus spectral period, and as we have already mentioned, MCE has been used for rock site, and DBE, design basis earthquake, is 50% of that MCE. Now, we should know that geotechnical properties or geotechnical characterization at that site. So, various borehole data were collected, only the typical borehole 1 and 2 are shown here for Kandla port. Similarly, for Mundra port also borehole 1 and 2 have been shown over here. You can see majorly it is a silty clay, followed by stiff clay, then silty sand, then stiff clay, then sandy gravel at Kandla port site. Whereas, so up to 30 meter depth, it is mostly a soft to stiff soil and mostly clay in between a very thin sand layer. Whereas, for Mundra port site, it is mostly silty sand, followed by stiff clay and then dense silty sand. All the SPTN value recorded at the site also are available. Using these values, one can get the shear wave velocity with respect to depth at this Kandla port site or Mundra port site. As I have mentioned, one can measure it using MASW or SASW or other field test, or in absence of that equipment, one can use the available correlationship between SPTN value and shear wave velocity to get this shear wave velocity values at those sites. Fine. Now, once it is known, next step is the synthetic ground motion. Which ground motion we are going to use for our ground response analysis. So, this is the synthetic ground motion. One can use the Bhuj earthquake motion, and the MAJ spectra is shown over here, which is recorded at the Passport Office of Ahmedabad, 2001 Bhuj earthquake data. And that program, this is a software program, RSP Match, developed by Abrahamson in 1998, which is available, is used to generate that synthetic ground motion, which will be compatible with that generated UHS at all levels of ground motion. That is, you have to select such an input motion for your analysis, which is compatible to that site. That is, either you use from the earlier historical earthquake data at that site, or use that synthetic ground motion or that synthetic motion which will be compatible with respect to that site based on this UHS. Clear? It is not that you can take any arbitrary value of this input ground motion. Clear? So, input properties are very important. First of all, geotechnical property as well as which ground motion you are going to use further. So, this is the mapped one. The previous one we have seen over here, the Bhuj time history, and next one shows us the design time history based on 2475 year of return period at Kandla port. Can you see a similar match, right? So, this is exaggerated form. You can see the Bhuj earthquake, which is the black line. Then level 3 ground means 2475, which is the red one. Green one is level 2, which is 475 return period, and the blue one is level 1, that is 72 years return period. That is the spectral acceleration versus time response. Now, we carried out this ground response analysis at this site Kandla port with the level 3 ground motion. I have already mentioned what is level 3. So, for different layers, layer 1, 2, 3, 4, these are the layer. You can see how the layers has been divided and what are the average value of the SPT and what are their description. Now, in this process, equivalent linear analysis was carried out. And for doing that, the computer program Shake has been used, Shake 91 version, which is developed by Campbell et al. In 1972 at UC Berkeley. It has been further modified. Now, latest version of Shake 2000 is also available. Okay. And you can see, for doing the equivalent linear model, you should have known what is the modulus reduction curve or the damping ratio behavior for individual soil layer which you are analyzing. So, either you can use the proposed or available design curves which are available with this Shake, like we have used for this Shake analysis of equivalent linear model, the model of Sun et al. 1988, which is valid for soft clay. Sun et al. Has given for soft clay what is the G by G max versus gamma behavior and what is the damping ratio versus gamma behavior. That model we have used. For stiff clay, we have used Vucetich and Dobrys model of 1991, which is already embedded in that Shake software. Also, in deep soil software, you will find these standard or these well known available literature modulus reduction curve and damping curve are available. But if you want for your own site, it is better to develop it through the actual soil property and use that modulus reduction curve and damping curve in your input model, right. Then Idris curve for medium silty sand and Vucetich Dobrys curve again for stiff clay were used, and for 4 different layers by considering 5% damping for the case of pseudo acceleration or spectral acceleration versus period plot, we got the result like this. Clear? So, how the amplification ratio can be obtained? Amplification ratio is nothing but at ground level divided by the bedrock. So, that is what for different 4 layer you can see this different amplification ratio versus frequency. You can see the black one is just line, horizontal line with value 1, because layer 4 is nothing but at bedrock level. Okay? So, layer 4 is at bedrock level. That is why there is no amplification, but other layers shows significant amplification, whereas layer 1 is a ground surface. You can see red color for ground surface amplification is this much, but in between the amplification ratio raises up to about 2.25. Can you see that? Whereas at ground surface it is only about 1.3. So, it depends on what type of material you have in between. Depending on that site response, you will get different amplification ratio at different level. So, somebody is founding or planning or proposing a foundation to in this layer number 3, then they have to be very careful about this amplification. Clear? So, what are the important observations we got from this analysis? Important observations like, for Kandla port, the contributing faults we got like F13, F25A and F14. Okay? Whereas, for Mundra port it is F25A and F13. For Dahej port, the responsible faults are contributing faults are F33 and F30. Whereas, for Hazira port it is F34. How you will get those things? Because at the beginning we have mentioned this fault map are available. You are using seismic hazard analysis and corresponding UHS coming from that. So, that will give you which fault is responsible. As I said, this F25 and F13 are responsible for Kandla port and Mundra port. Okay? So, as per IS code of 1893 part 1 of the year 2002 version, it underestimates the seismic ground motion for the 2 port sites. Why it underestimates? Let us look at this comparison table. Ground motion level 1, 2, 3. Level 1 means return period of 72 years, level 2 means return period of 475 years, and level 3 means return period of 2475 years. We know at which level needs to be used for which type of structure, that is known to us. Now, for Mundra port site, the peak ground acceleration we got these values, whereas IS code recommends for zone 5, which ports are in zone 5? This Mundra and Kandla, these two are in zone 5, whereas this Hazira and Dahej, these are in zone 3, right. So, when we are comparing the level 2 PGA, as per the IS code, the recommended value is 0.18 G. Okay? And what is the value we got from the analysis for Mundra port site, considering the soil properties at Mundra port? 0.19, which is very close to IS code recommendation when we are designing it for 475 year return period. Remember that. So, IS code we can safely use for Mundra port site when we are designing for 475 year of return period, but the same IS code is underestimate this value when we are considering the design for Kandla port. For Kandla port, the site response analysis gives us the value of 0.25 G, which is much higher than the IS recommended value even for the 475 year return period. Whereas, for IS code recommended value for 2475 years of return period is, for zone 5 it is 0.36 G, whereas for Mundra port site we got 0.33 G, which is very much comparable with respect to IS code. So, if we use basically IS code recommended values for Mundra port site, design is perfectly fine, but if we use the IS code recommended values for the Kandla port site as shown over here, using the local soil properties and the input motion, it seriously, the IS code seriously underestimates. So, we should design for this higher values. Okay? So, using this comparative study or table, one can easily find out what is the need to carry out the site response analysis before going for a particular design or important design at a particular site, because port sites are very important, port structures are very important, that has to be built for several years, that should not get damaged by any earthquake. So, that is why it is mentioned underestimates the seismic ground motions for 2 port sites of Kutch region. However, for Dahej and Hazira port, they are very much in good agreement. What are the other important observations we got from this case study? That is, for Kandla port site, the ground amplification factor is observed to be around 1.37 for frequency range between 1.37 to 2.1 hertz. Remember, this amplification also depends on your input frequency, that is what earthquake input motion you have used, what frequency it was having. If you use different earthquake motion, obviously this amplification factor also will change, and layer 1 has the higher value compared to other layers at all ground motion levels. Whereas, for Mundra port site, the value of amplification factor is ranging between 1.94 to 1.74, when the earthquake input motion is in the frequency range of 1 to 2.5 hertz. For Hazira port, the amplification factor is 1.86 to 1.91, and the input frequency range is between 2.2 to 2.74 hertz. Whereas, for this Dahej port site, the amplification ratio is 1.59 to 1.61 with an input frequency range between 2 to 1.1 6 HUDs. So, with this we have come to the end of our module number 8, that is site response analysis or ground response analysis. We will continue further in our next lecture.